Okay, so welcome to this session. So this session is the session in mathematics applied to economics and management. We have four speakers. The first one is Rita Pimentel from NTNU, and the title of her presentation is "The Green Halo Depth Effect. Is there any advantage of going green?" So the stage is yours.
Thank you very much, Carlos, for presenting me. And I would like to start saying that this work is based on a master thesis that two of my students that I was supervising this year, Jonas and Henrik, submitted. And with me in the supervision team, it was also Ana Jantarada, who is consultant, sustainable consultant, and Maria Lotvich, that she's also work here with me at NTNU. And the outline of my presentation, I will start motivating for the subject, why green bonds are important. And then I will explain what we have defined as green halo depth effect, and then explain which methodology we used and what are the main results. And finally, the conclusions and what are the next steps. And to start with, we know that the climate change, I think nowadays everyone is quite aware of that, is one of the biggest challenges that humanity is facing, and something needs to be done, and urgently. And one of the ways that, in fact, the climate change comes with what we call climate risks, and a lot of money needs to be invested in a way that we can stop this change in the environment. And then some kind of products were created, and green bonds is one of these products. There are other products as green loans, for example, and there are also other products not in the climate part, but more in the social part, for example, social bonds. But today we are concentrated only in the green bonds, and they were created exactly to face these climate risks. And the main difference between a traditional bond we call vanilla bond and the green bond is only the use of proceeds. What is the goal of what is that money for? And it can be used in many different areas. And for example, for clean transportation, for energy efficient, for controlling the waste or creating low carbon buildings. But essentially, when the bond is issued, it needs to be defined what is the proceeds, what is the main goal of issuing that bond. And as you can see on the right plot, the issuance of green bonds had increased a lot lately, particular in the last years, essentially from 2015, it increased 41%. It means that the awareness of the need of using this kind of products has increased. And we can say that Europe is the more mature market because they represent 54% of the issuance on green bonds. And also in the beginning, most of the green bonds, they start in 2007, but in the beginning, they were mostly municipality bonds. Corporate bonds, they only start later in 2013. But nowadays, they represent a huge percentage of the markets. And what kind of research is done in green bonds? There are different streams of research. There are one area, they study essential green bonds as a signaling effect. It means that in the moment that a company issues green bonds, it's giving a signal to the market that is a green company and it's committed towards the environment and creating value on this area. And another, on the other hand, mostly, there is a stream of research that is in greenwashing, studying if there are companies that they create, they issue green bonds, but essentially it's a misleading information because they are not really committed towards the environment. And we can also separate in two different markets, in the equity market and in the debt market. In the equity market, there are some studies where they are studying essentially when a green bond is issued, what is the impact in the stock market? And in this case, most of the studies, they see the impact in the returns, if there is any change in the returns. And some studies, but much few studies, they study the impact on the volatility of the stock, if there are changes, what we can call the risk of the stock. On the debt market, most of the research is concentrated in what is called greenium. And the greenium is essentially the differential between the green bonds and a matching vanilla bonds. We could create, we would need to find a vanilla bond that is similar to the green bond that is issued, in similar in ways of maturity and coupon and rating, and then compare if the yield of the green bond is lower than the yield of the vanilla bond, or equivalently, the price of the green bond is higher than the price of the vanilla bond. And this would mean that it's cheaper to issue green bonds than vanilla bonds. And most of the research in green bonds, it's on greenium. And our contribution, essentially, it's on the debt market also. But before I explain exactly our contribution, let me say that in the greenium, there are a lot of studies, but there is no much consensus. Some studies, they don't find any greenium at all. Some studies, they find positive greenium, and some studies even find a negative greenium. There is no consensus on the greenium effect, if exists greenium or not. And lately, practitioners have been saying that the greenium is disappear as the market mature, but this is from the practitioner side. And then what is the green halo debt effect? Essentially, our idea was, when you look at the greenium, you are looking at the green bond that is being issued. And you are seeing, more or less, if this green bond is more expensive than a corresponding vanilla bond. And what we do in this study, and to the best to our knowledge is not studied, it's we look at the portfolio of bonds that the company already has. And what we want to see is that when a company announces that it will issue a green bond, is there an effect in all the portfolio? Because if this effect exists, then it could mean when you are, first of all, it means that there is a halo effect, like the issuance of the green bonds has an impact in the equity market, but because other studies already found that. And now we would like to see if there is an impact in the debt markets as a whole and not on that exactly green bonds. And on the other hand, it can also mean that when you do the match with the vanilla bond, this vanilla bond, the yield of this vanilla bond is already lower because the halo effect already happened. As you see here in this plot, like we see the effect of the green halo when it's announced, the green bonds, and the greenium is calculated when the green bond is issued. Then there is a difference between these times, and our hypothesis that the green halo effect happened, then the vanilla bond that we will compare is already lower, and it's because of that people find a lower green or a non-existent green, because greenium should be summed with the halo effect on the debt. And how we do that? We apply an event study where the event is essentially the issuing of the bond. That can be a green bond or a vanilla bond. And then we need to calculate what is called the average abnormal standardized returns. Essentially, roughly, is we need to take all the bonds in the portfolio, and then we need to calculate the returns of all these bonds, but we need to standardize. We need to calculate the volatility of that bond and then standardize. And then we need to compare with the benchmark. We need to create different benchmarks of bonds, and we compare this abnormal return, but this return with the benchmark. And it's because of that that we call abnormal. And we also do the same study for cumulative average abnormal returns. In the event study, it's recommended to use the average abnormal standardized returns. We also calculate the cumulative only to have a sense of the yields, because the fact is, when we standardize the returns, it's not a yield anymore. Then we cannot get some numbers in the results, how the yield decreases or not. And then we compare these values, and we also, to avoid that the effect of this abnormal return comes from other reasons, and for example, characteristics of the bonds or characteristics of the companies, we calculate we do a regression model where we consider different characteristics of the bonds and different characteristics of the company itself. And the value green bond essentially is a dummy variable, where it's 1 if it's a green bond, and it's 0 if it's not a green bond. And first we have here some plots of the results. And on the right side, you can see that here it's only to see visually. We test statistically if it's positive, these returns, and they are different from 0 and they are positive. And what we saw also, what we realize also, it's that bonds that they are externally reviewed, because green bonds, they are still maturing, and there is now, European Union is defining a taxonomy, but until now there was no, and it's not finalized, in fact. Then until now, the companies, they would call their bond as green, and there was no mandatory review or something that you need to follow to say that the bond is green. But what we see in the results is that you can contract an external partner that will review your green bond to stamp that the bond is green. And in fact, the results are much preeminent when the bond is external reviewed. And also in the car plot, you can see that from day -1 to day 0, there is a small jump. I see Carlos.
2 minutes.
Okay, okay, 2 minutes. You see that there is quite a huge jump from day -1 to day 0 when the bond is announced. Compared the external reviewed with without external review, it's vanilla bonds and green bonds that are not external reviewed. And on those ones, you don't see the same kind of effect. From the regression model, we get this kind of results, and we did the regression with the green bond in general, and then with the green bond with external review. And as you can see, we can see some differences on the coefficient that we get. And from the car, we can conclude in terms of reduction, yield spread reduction, that for investment grade bonds, we get 2-3 basis points. And from high yield bonds, we get 8 to 11 basis points. To finalize, in this work, we could prove that there is a green halo depth effect. If we consider that this effect, because this effect, given that I'm looking to the portfolio of bonds, I'm looking to a company, we are looking at the secondary markets. if this effect goes to can be transferred to the primary market, then we can conclude that there is a financial incentive to the companies to issue green bonds. And essentially this work contributes to two areas of two streams of the literature. On one hand, it expands the studies on the debt side from the greenium, and also expands the halo effect not only in the equity prices. To finalize, we are now working to understand if this transfers to the primary market or not, seeing the next issuing, what is the effect. And also it would be important, this is a short time event, it's an event study. Then it would be important to see if this effect persists or not during time. Thank you very much for your attention.
Okay, so thank you, Rita. Thank you for your presentation. So if there is questions in the audience, you can write the questions in this Q&A, and I will ask these questions to Rita. Let me start asking the remaining speakers if they have questions for Rita. No? So I have a question. Rita, I understood the way that you have construct the study, but indeed I don't understand how do you construct the benchmark models, and how do you choose the bonds that you are analyzing?
Yeah, here I didn't have time to explain all these details, but essentially we extract a lot of bonds from the data set that is Thomson and Reuters, and then we construct the benchmarks based on two characteristics: the maturity and the rating of the bonds. And then we create 6 different maturities and the different rates, the A, AAA, etc. And then we did this kind of table connecting all of these, and then we will have all of these bonds in each one of the groups. And you need to be aware that the benchmarks, they will change from time to time, because sometimes you don't have bonds, they are not so liquid as stocks, for example. Then sometimes you don't have the values. Then every time that you want to do the study, in a point in time, you need to look at all the portfolio that you have of bonds, and then do this division and see how many you can calculate. And we only consider benchmarks if you have a minimum amount of bonds on the group. And then we calculate the average return of the bonds on that specific set.
Okay, I think that I understand. Let me see if I have another question, but let me see if there is a question from the audience. I think not. So you mentioned that there are other types of financial instruments, so like the social bonds or the green loans. There is another one for companies that want to move from brown to green. I don't remember the name of these bonds. So do you have any idea what is the effect that these bonds can make in the price, let's say, in the value of the portfolio of a company?
Yeah, I don't have a specific idea, but what I know is that, for example, social bonds, they are much immature than green bonds, because green bonds already have some time. But you really see in the market a change this year, starting last year. Probably because of the pandemic, practitioners start talking about that, and we want to investigate that further, but we still don't have data to do, because it's like 2 or 3 years of data. And here we start with data from 2007, then you have quite a span. But you see a change in the markets from green, and we are wondering if the change is from green to social, or green will continue and social will add to it. That's something to investigate further.
Yeah, that's very interesting, in fact. Okay, so thank you very much, Rita. I think that our time is over, so let's move on to the next speaker. That is, and now I need to see.
I think it's me.
Yeah. Okay, so can you share with us your presentation?
Sure. I think
So
I'll
the
share
next
the desk.
speaker is Alexandra, and the title of her presentation is Obtaining the Optimal Reinsurance Treaty of Several Dependent Risks in Practice. So it's a completely different topic, but still in the area of economics and management. So the stage is yours.
Thank you. Thank you, Carlos, for the nice presentation and for inviting me to this nice session. Indeed, it's a different subject from the previous talk, but within the applications of economics and management, in this case, insurance and reinsurance. So this is a work that I have been developing with a colleague of mine, Manel Guerra, also from ISEG. So I will just briefly introduce the problem of insurance and reinsurance. For some of you, it might be new, and then I will develop our results. So first of all, I mean, this is the motivation for all these quantitative financial models. More and more quantitative risk models are vital for financial institutions, not only for risk management, but also because of regulation. So there is nowadays a lot of regulation aimed at financial and insurance institutions that has to be enforced. And for this regulation implies that many quantitative analyses have to be made. Also, what we have developed, what is really, well, there are several originalities, I think, in this work, but one of those is that we include dependencies. Dependencies are hard to deal with, and but they are known to play an important and determinant role in risk assessment. So when they are neglected, we are not measuring risk as we should. Okay. So what is insurance? Given a risk that we will denote by X, it's a random variable. Okay. The idea is that the policyholder pays a premium to transfer the risk to an insurance company. So we pay a premium, and if there is a loss, the loss is paid by the insurance company, or part of the loss. Now it depends on the terms of the contract. Okay. So the premium is named premium because it's paid a priori, before we know if there will be a loss and how much will be that loss. So we first pay the premium, whatever the outcome will be. There are several ways of computing premiums. So the premium is the price of the insurance, basically. I will just include here some examples that are premiums based. So basically the premium includes a part that is the expected value of the loss, and it has to have a loading above that. So it's not enough to price an insurance as the expected value of the loss. If the insurance company would do that, it would bankrupt. So it's mandatory that there is a loading to that expected value. And the way we compute this loading is what defines the premium, and it's what differentiates the premium calculation principle. So for instance, when we talk about expected value premium calculation, we are saying that the loading is computing based on the expected value. So in the case of the expected value premium calculation, the loading is just constant times the expected value. If it is the standard deviation, then the loading is computed based on standard deviation or the variance and so forth. There are premiums that are not moment-based. So there are premium calculation principles that are not moment-based. Here, we will focus on moment-based premiums. So this is just to introduce the problem. And now we have reinsurance. Okay, what is reinsurance? Reinsurance is something. It's a type of insurance. It's when the insurance company that has kept the loss, okay, or the risk, basically, okay, the insurance company now wants to transfer part of the risk to another insurer, okay, and this is reinsurance. So the idea is that the risk that is now in the insurance company is transferred, or part of the risk, so a function of the risk that is between 0 and X is transferred to another company. Of course, how does the insurance company do that? The insurance company does this by paying a premium. a premium that is computed based on the ceded part of the risk. So reinsurance comes at the price. What is the benefit of reinsurance? It is a risk management tool, because by transferring part of the risk to another insurer, the insurance company decreases its risk. So it's a risk management tool. It's a very important risk management tool in the insurance companies. Okay, so here I show just two types of reinsurance. These are the most common ones, and it's just to have an idea what reinsurance is. So imagine that the risk is this blue line. It's X. It's just the graph of X, right? It's the total risk. We can transfer a proportion of the risk. For example, the so-called quota share reinsurance, where we transfer a proportion, a percentage of the risk to the reinsurance. Or we can transfer a non-proportional part of the risk. For instance, the stop loss or the excess of loss, where we keep all the risk up to a certain amount, M, and after that amount M, we transfer it to the reinsurance company. So these are just examples to have an idea, okay? So these are just two examples of function Z. Function Z is the ceded part of the risk that we transfer to the reinsurance company at the price of the reinsurance premium, okay? So now what is our goal? The thing is that there are two main questions in reinsurance, and that's why this problem has been so studied for many years, and it still is. It's an active field of research, the optimal reinsurance problem. Why? Because there are two questions arise when we talk about reinsurance. One is, how much reinsurance should we do? We, and by we, I'm in the position of the insurance company. So I'm the insurance company. How much reinsurance should I do? And what type of reinsurance should I do? Okay. So of course there is a trade-off, because reinsurance decreases my risk, the insurance company risk, but it also decreases my profit because I have to pay the reinsurance premium. Okay, so there is a trade-off, and this leads to the optimal reinsurance problem. So what is the goal? The goal is to find the insurance strategy that optimizes something. And obviously, depending on what we want to optimize, we will have different solutions for this problem. Okay, so we have to define the measure of the underlying risk that we want to optimize. Okay, in our set, in our work here, what we have considered is this. We have considered that that the insurance company has several dependent risks. Okay, for instance, lines of business, and the dependence is general. So we are just assuming any joint distribution for the underlying risks. Okay, we are also considering general insurance contracts. So any function, the only restriction for this function is that, I mean, the Z is the ceded part of the risk. So it has to be between 0 and X. Okay, so any function, really?
Yes.
I've been talking for 15 minutes.
Yes. No, you have 2 minutes, yeah.
Okay, thanks. So any function can be, any function is allowed in our set. Okay, we consider one-time single periods and general moment-based premium calculations for the reinsurance. Okay, so we're now dealing with the reinsurance problem and independent negotiation of the reinsurance contract. Okay, the goal is to maximize an expected utility. Okay, so this is our settling, our problem. So moment-based premiums, and we want to. So this function L is our profit. Okay, so the incoming premiums minus what we pay if there are losses. Okay, with reinsurance we pay less because we transfer part of the losses to the reinsurance company. Okay, and we want to maximize the expected utility. For instance, the exponential expected utility, that is the simplest one, but it can be any any utility, okay? And what we have shown is that the solution to this problem exists, so there is an optimal solution. And also we have obtained necessary optimality conditions, okay? And it's nice to see these necessary optimality conditions. This psi is the premium, the reinsurance premium. So the necessary optimality conditions show us that there is a trade-off between the risk we transfer. I'm just finishing.
No, sorry, Alexandra, you have until, sorry, it's my bad. So more 5 minutes, sorry. No, that's my bad, sorry.
So how much do I have? I was finding.
No, you have 5 minutes yet. Sorry.
I had 7. Okay, thanks. Anyway, I have to real. So basically, the interesting part is one of the main. So the main result was the existence of optimality treaty, and these necessary optimality conditions. And these optimality necessary conditions show us a trade-off between the premium for each risk and what we transfer for each risk and the other risks, okay? Because one point here is that we assume that the insurance company negotiates the reinsurance independently for each risk. So I know my risks are dependent, but I will negotiate the reinsurance independently. So basically the reinsurance company does not know I have dependencies here. And these optimality conditions show that trade-off. So psi is the reinsurance premium. So now these are just the examples for the expected value reinsurance premium and various related premiums like the standard deviation of various reinsurance premium. What we did next was, let's use this optimal. So, you know, practitioners look at these results and they say, yeah, so what? So they want a way, they want us to give us, or they would like to see a way of, okay, what is my optimal reinsurance treaty? So how do I compute from these conditions an optimal reinsurance treaty? And what we did was we have looked to these optimality conditions and we rewrote them as a fixed point problem, okay? So basically we have shown that, so this is the function here in the optimality conditions. If we put this expression to the left-hand side, basically you have a function that can be either positive, negative, or equal to 0, okay? If it is positive, then the reinsurance treaty, sorry, I have to, okay. If it is, I cannot, no, I can, sorry. If it is positive, if it is negative, then the reinsurance treaty will be transfer everything. If it is positive, then the reinsurance treaty will be do not transfer anything. And if it is 0, the reinsurance treaty will be the solution of this equation, okay? So basically we have shown that this equation is strictly decreasing, so it has a single 0, okay? So it means that we can transform the problem into a fixed point problem. So the reinsurance treaty that satisfies the optimal condition is the one that is a fixed point to this function here. So we have here the derivative of the utility and then first moment, second moment, etc., up to the case moment that we need for our premium. Okay. So by transforming this into a fixed point problem, we can use it very easily to obtain a numerical scheme based on this fixed point problem. Okay, so basically at a certain point, what we do is we fix the treaty for every risk except one, and we find the fixed point for that one, and then we do that recursively to all risks. Okay, if we want to use Newton algorithm, we have to have some attention because this function is not necessarily differentiable because of our constraint, because the seeded risk has to be between 0 and x. Okay, but with some penalty functions and some regularizing, which regularizes our function g, we are able to apply Newton's algorithm and to compute the Jacobian of this function. Okay, so just to finish a numerical example, we have considered first two risks. One that is that is light-tailed and exponential, and another one that is heavy-tailed, a Pareto. And we have considered dependencies through Frank's copula, but here dependency can be anything. Okay, we just need a joint distribution. We have used Frank's copula because Frank's copula allows us to have both negative and positive dependence. Okay, and in green we have the optimal solution for positive dependence, and in red we have the optimal solution for negative dependence. In yellow we have the solution in the independent case. Okay, so we see that dependency plays a role. Okay, so we have different optimal treaties according to the dependency. Also, we can see that the treaties, especially here in the expected value, the treaties for the light-tailed and heavy-tailed are quite different. Okay, so dependence does play a role here. We can also see if we have a more intricate dependency, because we just need a joint distribution. If we have a more intricate dependency, we have quite interesting and strange, let's say, optimal treaties. So this shows that dependencies break intuition on the optimal treaty for insurance here. Thank you very much. I'll finish here. Thanks.
Thank you, Alexandra. So very interesting talk, and sorry for my interruption.
No worries.
I was looking to the program, and the program just has the slot of 15 minutes. So, well, never mind. So
no
let's see if there is questions from the audience. It seems not. So let me ask the remaining speakers if they want to ask anything. I have 2 or 3 questions, but if there are other questions, okay, no. So let me ask one thing, because I think that I have lost some part of the presentation with this story of the schedule. So you are optimizing in one period of time.
Yeah.
In a fixed period of time.
Yes, usually insurance and reinsurance are contracted in periods of time, usually years, but not necessarily. So we are doing this, for one period.
And do you know what happens immediately after that? Because this is always a problem, right? So when we do this optimization,
yeah, I'll do for reinsurance. When you optimize in a fixed time horizon, you always forget what's next, so you can bankrupt but in insurance, basically what we say is let us consider the risk for 1 year, and this is the risk for 1 year. So I don't know what will be the risk next year. Okay, so this is the amount of risk I, as an insurance company, have incurred for this year, or have in my responsibilities for this year. So for these risks, because also the insurance company buys risk usually by periods of time. Okay. So for this period of time, I have these risks. What do I do with it? How much should I reinsure? So this is the problem. This is actually more interesting, the interesting problem from the practical point of view, because that's what happens in practice actually for the insurance and reinsurance companies.
Okay, so I have just one question. I think that must be short, the answer, but so in these examples, you choose a specific copula, right? But
yes, for each example. So here I have 3 copulas, for instance. Yes.
Yeah, but if with the same data, if you change the copula, the results are different.
This is the same data with different copulas.
Okay.
This is the same, always the same risk, and exponential, and the same Pareto, the same exponential. This is a Pareto and then exponential with expected value 1. So we can compare them.
Okay.
And with the same loadings, the same premium, everything is the same. The expected utility, the only thing that changes is the premium calculation. But for the same premium calculation, also we do several and the dependencies. So we change premium calculation and dependencies, but we can see that. It varies, and you see here. I'm not sure you are still seeing the slides.
Yes.
But it changes completely with. So you see, the green line is positive dependence, the red line is negative dependence for exactly the same problem. And here it changes more because it's a more strange copula.
So basically, depending on the type of dependence between the risks, the strategy can be completely different.
Completely different, yes. Yes, and non-intuitively. That's the interesting thing about dependence.
Yeah. Okay, so thank you, Alexandra.
Thank you.
Igor, maybe you can share with us your screen.
Let me see. Okay. One second.
Are you able to,
Sorry,
share?
yes. One second. Just let me choose. I think it's this one. Okay.
Okay, so the next speaker is Igor Kravchenko, and his talk is about switching between investment projects and an optimal stopping problem. So the stage is yours.
Okay. First of all, thank you very much for the invitation, Carlos. It's my pleasure to speak at this section. Second of all, you can see my mouse, right? There's no problem. Yes.
Yes, we can.
Yes. Okay. Fantastic. This is the joint work precisely with Carlos and with Claudia, who will speak after me. And I will be talking about the management problem. Then the company has two different projects and decides how to behave between switch between this project and how to behave in the investment environment. Okay, so this is the simple structure of the talk. First, I will give a simple an economical motivation. Then we'll design the mathematical framework. Then we looked at the switching problem. This is when the company is already on the market and decides what to do, how to behave, when it is optimal to switch, when it is optimal to stay, when it is optimal to exit. Then we will look at the investment problem. This is the problem when the company is outside of the market and decides to enter in this environment, in which project to invest. Okay? So let's dive into economical motivation. So what we have here is we have two projects. The project one will be the risky one, and the project two will be the more conservative one. At each point of time, the company has the possibility to switch from, let's say, if it's in a project one, switch to the project two and pay the cost K12, or it has opportunity to exit. So this means since these costs are not negligible, this is not optimal for company to do constant switching. So the switching will be punctual. This means that our optimal at each point of time, company has three possible states. It's either in a project one, either in a project two, or it exits. The exit is permanent. So once the company exits the market, it cannot re-enter the market. So we have only one point of one source of uncertainty. This is the price. So it each determinant price, it each fixed price, the company has to make a decision. We model the price as the geometric Brownian motion, and why the projects are, why we divide the project by the risky one and the most conservative one, it is by the instantaneous payoff. So when the company is in the project one, it receives the instantaneous payoff of pi1, and you can see that the pi1 slope of the pi1 function is higher than the slope of the function pi2, the conservative one. So obviously, if the price is higher, we would prefer we prefer the project one. If the price is lower, we prefer the project two. So this is our model. What will be the expected payoff of the given strategy? The expected payoff of the given strategy will be the combination of three terms. First, it will be the production term. This means that when the company is producing either in a project 1 or in a project 2, it receives the payoff, and obviously it is discounted by the discount factor. When the company makes the switch, it has to pay the cost key 1, 2, and if it's switching from 1 to 2, or key 2, 1 when it is switching from 2 to 1. So this is the additional cost that the strategy has at each given point of time. Once again, these times are discrete. And every time the company decides to exit, it pays the cost kx. It is easier to consider this cost to be positive. It is not necessary, but it is easier to see this problem like this. Okay. Now, how do we solve the problem? We want to find the optimal strategy that maximizes this functional. Okay. So as we saw before, we have 3 possible states: the state 1, state 2, and the exit. The exit state is not an interesting one, so we're not considering it. So our solution will be to find these functions v, what company should do at each point of time for this price. Okay, so how do these problems are usually solved? They are solved by guessing the solution. Why it is done like that? It is because we don't have the construction for the solutions. Basically, what we have is the verification theorem that tells us if our function satisfies Jacobi-Belmont equation that I will show you later. If it satisfies some regularity conditions, then it is a solution. But we don't have the method of construction of this solution. So basically what we do, we first guess the solution, then we check if it satisfies HG equations, and then we kind of feel smart and happy because we have solved the problem. So there is no construction method. Okay, for this problem, let's see a little bit how we can represent this solution schematically. So for the project 1, for example, what happens in this solution? Well, this solution is never optimal once we are in the project 1, it is never optimal to move from the project 1. If we are in the project 2, if the price is high enough, it is optimal for us to switch to the project 1. So this is kind of not very interesting solution, but it is still possible. There is another solution that is more interesting when we add a little bit of, we add exit. So if the price is low enough, there is a point from which it is optimal for us to exit, either from the project 1 or from the project 2. And once again, it is optimal to switch up and when the price is high enough. We call this solution of type 1. Okay, so these are our Hamilton-Jacobi-Belmont equations, and these equations divide the space in the sense that these are coupled, nonlinear, coupled quasi-variational differential equations. They are coupled because you can see that V1 is dependent of V2 and so on. At each point of time, only one of these equations is equal to 0. And which is equal to 0 gives us the region, what is happening in this region. For example, if the equation 1 is satisfied with 0, we are producing. If it's 2, it is optimal to switch. And if it is 3, it is optimal to exit. There is another very interesting region that is Hysteresis Region. This means that if there is the point from which it is optimal to switch from project 1 to project 2, automatically the extra point will appear. An extra threshold will appear. This means, we denote this region between these two is a Hysteresis region. This region is very interesting because it cannot be accessed continuously. For example, if you are here, it is optimal to switch, then you're producing somewhere here, then you go up, and so on and so on and so on. You see, you cannot access this region directly by continuous operation. However, you can start here. Or, as we are all in the COVID-19 pandemic, you can have a high shock and you end up here. This region is very interesting in the sense that you wait here to see what happens. If the price goes high enough, then it will be optimal for you to switch to the project 2, less risky one. If the price goes down, it will be optimal for you to exit. There are a lot of companies at this moment that are making exactly this decision. Okay. Now, these are Hamilton-Jacobi Belmont equations just represented. You can see that at each point of time, only one of them is 0. This will give you here, for example, it is optimal to exit, then hysteresis region, then continuation, then again. Okay. Now, how does these solutions look like? These are polynomials of the positive and negative, the sums of polynomials between positive and negative degree. You can see that here, for example, we have the function v2 starts higher, and then it becomes lower, and it will be optimal here, for example, to switch from k to 1 to switch from the project 2 to the project 1, and so on. Okay, and these are how the solutions look like, and this is exactly how we solve them and how we find them. So our method of solution, we guess that the solutions look like this. Then we do value matching. This means that we value matching between these two parcels of the equation. Then we also have to satisfy the continuous of the derivatives. This is smooth Bayesian conditions. We solve these equations. We show that under the certain parameters, they satisfy Hamilton-Jacobi equations, and then we know that this is a solution. Okay, another thing that we can do, we can classify the parameter space. In the sense we can see if, for example, what this proposition says is that if there is an exit, okay, so we have to bound our strategies, optimal strategies to the strategies that there is exit. If there is exit, then we can find the constant for this K21, the bounds for the K21 and K12, in order that we can classify which type of solution we will get. So, for example, if it is under these bounds, the solution will be of type 2. If it is on some other bounds, the solution will be of type 2. So basically, we can also characterize the perimeter space. So this completely classifies the problem of switching. Once again, the company is already somewhere on the market and decides the optimal strategy. Now that we know all of the optimal strategies, we can kind of step back and see what the company will do during the investment problem. So now the company is deciding where to invest and when to invest. It can either invest in the project 1 and pay the cost K1, or it can invest in the project K2 and pay the cost K2. Obviously, the problem remains the same. Once the company is on the market, it may switch between the project. Once again, we can write it as an optimal stopping problem. This one is only one-dimensional because, in fact, what we have to do, what our function will be, it will be the maximum between this costs of investment. Okay. What are the possible strategies here? For example, imagine these were
minutes, Igor.
Thank you, Carlos. So what will be the optimal strategies here? The optimal strategy will be to invest in the function v1 and never invest in the function v2, because you can see the function v2 is only higher when the cost of investment is negative. So basically, this is the simple solution. Okay, there is another more interesting solution. When it is optimal, invest in the project 2 between these bounds, gamma 1 and gamma 2, then wait between gamma 2 and gamma 3, and then invest once again in the project 1. So these are the two interesting strategies. In order to eliminate other non-interesting strategies, we kind of set some economical bounds that are very, very clear. For example, you can the cost of investment cannot be higher than the cost of exiting. So either you enter, then you exit, and you receive extra money, and there is no kind of the automatic switching. It should be optimal to enter directly in the project 1 instead of entering in the project 2 and paying the additional cost of switching out. If we eliminate this, once again, we are able to characterize our parameter space. This means that we can set the bounds K2 plus and K1 minus that bounds our solution. And we are able to say if our parameters are in this interval, the solution will be of type 2. If they are on the other interval, the solution will be of type 1. There is also an interesting side effect of this proposition that when we started this project, there was a large, very interesting question: is it possible to invest? Is it at any time optimal to invest in this hysteresis region that we described about? The answer is no. It is never optimal to invest in the hysteresis region due to the structure of the problem. So this is it. Obviously, what it will be very interesting is to try this on the real case if managers actually decide and choose the optimal strategy under these conditions. And I think this our social context will help us to make this research possible. There will be a lot of examples that we can study. Okay, so these are the main references in our paper. Okay, so thank you.
So thank you, Igor. Let me just see if there is questions from the audience. So please feel free to ask questions in the Q&A. The remaining speakers, do you have questions for Igor? Okay, so I will make a short question because we have just two minutes until Claudia starts speaking. So you talked about the hysteresis region, and you said that continuously we cannot attain the continuous the hysteresis region. Why? Because in fact, if we are in that model, or we are producing, or in mode 1 or in mode 2, and there is that that movement between the two modes, and we never attain the hysteresis region. So we can attain through like a discontinuous movement, like a pandemic, as you said. So what is the relevance of the hysteresis region in a case like this? I mean, well, I'm one of the co-authors, so I know that we have some simulations about the time that we can spend in that region. Do you have something in mind about this?
I don't know what you mean by your question, but I can try answer anyway.
No, I mean, so we have computed, for instance, the probability, the expected time that we will be in that region, and so on. So my question is if the region is relevant in this sense.
Yes, of course it is relevant, and depending on the parameters of the problem, you can stay in that region for a very long time. So as you know, there are examples, and depending, there also the possibility that how do I say, is you can probably depending on the parameters, depending on your variation, especially on the variance, you stay in that region for longer or for the shorter time. Mm-hmm. So if initially your process didn't have a large variance, then once you get in this hysteresis region, you can stay there for a very long time. So, and if the process has larger variance, obviously you will be switching from there very quickly.
Yeah. Makes sense.
Okay.
Okay, Igor. So thank you very much for your talk. So Claudia, can you share with us your screen?
Yes, let me try.
Thank you, Igor.
Okay.
So the next speaker is Claudia Philippart, Claudia Nunes, as you want.
Sorry, because it seems that, okay. Okay, no, it's done.
Yeah, it's fine. And the title of her presentation is Optimal Stopping Problems with Levy Process. So you can start. Thank you.
Thank you very much, Carlos. Just a quick question. Do you see full screen or?
I think no.
No.
Okay.
I think you have to share the screen
No,
and not only the PDF.
Better now or not?
no, it's the same. You can do Control L.
And now?
Yeah.
Yeah, is it working now? No.
I think no. I cannot see. Alexander, you can see? Can you see?
No, it's black now.
Let me
I think if you share the desktop instead of just the PDF,
do you see?
yes, it should work better.
Yeah, now it's much better.
Yeah.
Yeah.
Okay, so after this technical issue, thank you very much, Carlo, for inviting me for this session. And also I would like to welcome all the speakers, my fellow colleagues, and also everybody that is attending. I decided, of course, that you have already had a kind of taste of the problems that I will be discussing now with the presentation from my colleague Igor. So in the last years, I've been doing research regarding optimal stopping problems, which are related with investment problems in more in economics, which is the main field of applications that I'm dealing with. But at the bottom of the problems, those are optimal stopping problems. And I would say that one part of my participation in terms of research has been with levy process. And so I decided to bring to this more extended talk to give you a kind of a taste about what kind of questions we have when we are dealing with levy process. Yeah, the problem now is that, okay. Now, I will just make a motivation, and I will also talk about very briefly about levy process. I will also talk about, in general, these optimal stopping problems and their relationship with free boundary problems. Then I will show you 3 applications that are all related with technology innovation problems. 2 of the applications I'm co-author of the papers, one of them I'm not, and it's one of the most cited one, and it's quite interesting also and easy to understand. And then I will take some conclusions. So that's the outline of the talk. Now, using also what you have heard in the last presentation, the idea is to find a time to take some decision, where by decision we mean investing or switching or exiting or whatever. So we need to define what is an action, but what we want is to find, in general terms, what we call an investment problem. And by investment, we mean that we want to maximize the expected value of future profits discounted by time, which is exactly what you have in the first part of this expression, this integral. And then when you decide to take this action, which let's call it investment, you pay or receive a lump sum, which here is denoted by the H function, always discounted back. And X is your underlying stochastic process that may represent whatever you want, all the uncertainty or part of the uncertainty related with the process. And this stop is a stopping time, and it has to be adapted to the filtration generated by the process X. And therefore what we need, and this X, by the way, is Markovian, and therefore you just need to keep track of the last value of the process that you observe, that without any loss of generality, you may assume to be seen observation obtained at time 0. So this is what you want to solve. And in this presentation, so you've seen with Igor's presentation that the underlying process was a geometric Brownian motion. A geometric Brownian motion is a very familiar process, mostly, especially to people that are working in finance and also in economics applications. And one of the things of the property that it has is that it has continuous sample paths. But as the pandemic situation, which is now the example that most of us are using to illustrate our research, but as the pandemic shows, sometimes we have jumps. Well, these jumps, they are not clearly jumps, but they are sudden increases or decreases in the level of the process. And therefore, we want to be able to say something about process who have this characteristic of having these jumps, which in mathematical terms we see as a discontinuity. And that leads directly to the definition of a Levy process. So the definition of a Levy process is quite open, I would say, and it's basically just a process which sometimes you hear say about that has CAD-lag sample paths. It means that it has sample paths which are right continuous with left limits, and the increments are stationary and increments and independent. So it's a kind of a broad definition for a stochastic process, but being stationarity and independence quite important because it allows us also to use some of the machinery for stationary process. And okay, of course, that is right continuous but with left limits. It means that it's in order to take into account of jumps. Now, in fact, what is interesting is some examples. I'm sorry, just give me 1 second. That's the problem of being at home, is that we have interruptions. Não pode haver barulho. Sorry. Okay, sorry. So examples of Levy process, they are quite familiar for some of us. The Brownian motion is one of example, and in fact, it's the only process that has continuous sample paths that is a Levy process. Another example is the Poisson process and the compound Poisson process. So those are three processes that mostly for people that use that work in stochastic process, they are used to handle. I will be particularly interested in this class of process, which is exactly arithmetic Brownian motion. So this is this part plus a sum of, in fact, it's a sum of jumps where this NT is a Poisson random variable with rate intensity, with parameter lambda t. So what I have is that this W is a Brownian motion. Mu is usually known as the drift. Sigma is the volatility. And this NT for all t is in fact a Poisson process with intensity fixed equal to lambda. It's independent of the Brownian motion. And this is a sequence of independent and identically distributed random variables. And this is exactly one of the processes that people working in Levy process, in particular with applications in economics, deal more often. And in fact, if you compute the exponential of this process, which is more or less the same kind of thing that moving from Brownian motion to geometric Brownian motion, you also compute the exponential. Now, instead of just computing the exponential of the Brownian motion, we are computing the exponential of the Brownian motion with the drift component, plus the jumps, the influence of the jumps. And then when you do this, you end up what it is known in the literature as an exponential Levy process or a jump diffusion process. By the way, the term jump diffusion is used in the literature in a more, it's not so restricted to this. It's also used we don't say exponential or Levy process. We say jump diffusion, and it fits all kinds of examples with drift, without drift, etc. Okay, so this is the framework of most of the applications that we find in optimal stopping problems. Okay, so what is this jump diffusion process? What is the main features that are interesting in terms of modulation? First of all, it means that between jumps, the process evolves like a geometric Brownian motion. And geometric Brownian motion, it's an easy process in terms that it leads to some equations and some formulations that can be analytically solved. So this is a plus. Now, this is between jumps. Every time there is a jump, the jump impacts in the level of the process by a multiplicative way. It could be also a sum, but in this formulation, it is a multiplication. And it means that impact is proportional to this exponential of the jump, of the magnitude of the jump, that in general can be a random variable. And of course, that most of the cases, these jump represent rare events like crashes or pandemics, or as we've been seeing in the last years, like for instance, when we had the financial crisis that led also to the economical crisis in 2008, now with the pandemic. So or even with, for instance, when we had the 9/11 attack. So most of the cases, those jumps, they are not frequent events. They are more related to I would not say only extreme, but more rare events. And these jumps are driven by a Poisson process with intensity rate lambda. So this is the definition, or that's the interpretation of the jump diffusion process. One thing that we need, and in the last presentation we have already seen, is that it's the way that we solve these optimal stopping problems. We use tools that are related with the fact that the process is Markovian, and for Markov process, we may define the infinitesimal generator, which is nothing more than the expected value of the increment, an infinitesimal increment of a function of my process X. And this has to be, of course, that in case this is well defined and it belongs to C. In case you have a jump diffusion process, then you just need to use a particular form of the Ito's formula, that takes into account also the existence of jumps. And in that case, you end up with the infinitesimal generator, which has this component, which is due to the diffusion part, which is the continuous part of the process. And then you have a contribution from the jump. And this contribution, I denote by capital F, the distribution function of the jump sizes. Although in some cases, these jump sizes can be also deterministic. And in that sense, if it is deterministic, this is no longer integral, but it collapses to just the difference between the function at the current point plus the jump minus the function at the current point. So this is the infinitesimal generator. Okay, so going back to these investment problems, when you have these investment problems, or when you are also solving any stopping time problem, in fact, this is a particular case of a stochastic control problem, where here you just have one control, and the control, as soon as you activate the control, the process ends. So it means that you have two possible actions. Either you continue, and in that sense, if you continue, you get a profit. I wrote equal to G, but in fact, it should be a pi, which is like a running payoff. It's what you get if you are just keep going the process. And I denote by D the set of values where continuation happens, or by some reason, and that's what we are looking for, is to find the reason, the state that for which it's optimal to stop and take the action. And the action may be investing or switching or exiting or whatever, okay? So it just needs to be well defined. And as soon as you stop and take the action, you get this reward H, which can be either a cost or a reward, and you denote by S set of values where stopping is optimal. Now, as we are assuming that the underlying process is Markov, it means that when you are looking at the process, if you want to find out if you should continue or if you should stop, you just have to keep track of the current value of the process. So you don't need to keep trace of all the sample, of all the evolution of the process, because being Markovian, all the relevant information is contained at the current time. And then we'll denote by tau star the first time that you cross, you move from the continuation and you enter in the stopping region. Okay, and that's the stopping, that's the time that I'm looking for. Of course, that is being a stopping time, it means in particular that it is a random variable with specific characteristics, but nevertheless it's a random variable. So this definition, of course, it has to be written, it has to be understood in a specific sense. And being a random variable means that I would like to know what is his density distribution, its first, second order moments, and so on. Now, the thing is that this random variable is very difficult to find out, in terms, not to find out, but to characterize. Even in some cases, I may be able to find the expected value of this random variable, but it's not very informative, because experience with other problems shows that this stopping time, this random variable has a large standard deviation, and therefore the expected value is not very informative. And therefore, instead of looking for this to characterize this optimal stopping time, I'm looking at to find out what is the boundary of this stopping set S. And then I will just use this definition to as it is. So I will define this tau star as the first time that I enter my stopping time, my stopping set S. Okay, now on top of that, the problem is that I don't know neither the sets, the stopping sets, neither the continuation set. Otherwise, the problem would be, at least from mathematical perspective, would be solvable. So, as I don't know this, in fact, one of the tools that we use, which is used in a dynamic, in the dynamic programming principle, is that we are able to reduce this problem to a free boundary problem, where in the continuation set, this equation, which is in fact is a partial differential equation, eventually with this integral operator due to the jumps, needs to hold. And for the stopping set, what happens is that if I take the decision to stop, I get, I earn this profit, or I pay this cost H. So for the solution is clear for the stopping set, but I don't know where is my stopping set. And this, as also my colleague from the previous talk mentioned, this is the Hamilton-Jacobi-Belmont equations, which we call for short HJB. And therefore, in order to solve these problems, one of the techniques that we use is to find the corresponding HJB equation. Now, the HJB equation, as it is written, it does not lead to necessarily to just one solution, due to this differential operator, because this differential operator may have several solutions, but the solution to the optimal problem is unique. And in fact, using a verification theorem, which again my colleague mentioned in the previous talk, we are able to choose amongst the proposed solutions of the HJB equation, which is the one that is solution to my optimal stopping problem. And therefore, basically, we need to solve this differential equation. We need also to propose or to find somehow what is this stopping set S and this continuation set D. And then with a proper verification theorem adapted to the conditions of my problem, choose the only one that follows all the conditions of the verification, and then in that case, I will have the solution of the optimal stopping problem. So this verification result, in particular, and because of exactly due to the fact that I have a differential equation, gives me or should give enough conditions in order to have a unique solution. For instance, I show you in these two plots what happens. Imagine that so in this left panel, I have a problem where my underlying process, my jump diffusion, really has this diffusion part. And when it has a diffusion part, what I need to do is that, okay, so imagine that this capital G, in fact, is what I call previously pi. So this is my running payoff. So I want to define where my function, so it's not my running payoff, in fact, it's my terminal cost, which I call H. Sorry, I didn't change this notation because I took these figures from one very nice book on the subject from Pesquet and Shirayev, and they use other notation. So, but okay, so imagine that this is what I get if I take my decision to stop. Now I need to find an envelope of this function such that the envelope leads to a continuous function, which is fine here, but it also needs to be smooth everywhere, which is not the case. So therefore, what I'm looking for, if this would be the case, is a pair of conditions of points A and B, such that when I glue this bit with this function, the terminal cost, I have a function that is smooth everywhere. And that's what I need to do. Now, if I don't have the diffusion part, I don't need to have smoothness, but I need to have continuity. So I need to look for the pair A and B of points such that I'm able to glue the function which I'm looking for, this value function, in such a way that it glues continuously in A and B, because it glues continuously everywhere, because everywhere this is my function G, which is well defined, and this is the solution of in this case of a differential equation, and in this case of a difference equation. So this is by construction continuous everywhere, but it could be discontinuous in the boundary, and therefore I need to find enough conditions so that this is also continuous. So graphically, that's what I need to do. Okay, so it means that I have a kind of algorithm to solve the problem. So I find the HAB equation, which is kind of very simple because I just need to find the infinitesimal generator and plug it in here. Then I need to propose a stopping set and a continuation set, provide enough boundary conditions so that I get the only solution of my stopping problem. And on top of that, there is also other conditions like more limit conditions that for this presentation, I will just skip. So we have a kind of basic algorithm, and therefore saying so, it seems that this should be a problem easy to solve. Now, the problem is that it's not easy. So finding the HAB equation, it's easy, but then the rest of the steps, it's kind of problematic. So already solving the integral differential equation could be a problem. Proposing a stopping set and a continuation set, I can always propose, but I can have a wrong feeling about that and propose a solution that it's not possible. I need to provide enough boundary conditions and check also these other conditions from the limit equation conditions. So what I want to show you, and that leads me to the part that I would like to see with you, is how do we do this in particular cases. And the applications that I have in mind, they are very much driven by questions regarding technology innovation. So in most of the papers and literature of the subject, you find a lot of examples. And I think that most of us are quite sensitive to these examples because unfortunately we are living in a world with a huge appeal for new products and consumption. And as consumers, we also know that every time there is a new version of iPod, iPhone, or a car or whatever, we are looking to change our old, to sell our old, or to just put in away and buy the new one. And therefore, innovations, they are important also to keep the demands. So companies like Apple, for instance, they invest a lot of innovation because they know that as soon as there is an innovation, there is a jump in the demand of products. So this is an example, but there are more examples regarding technology innovations. And therefore, companies, they invest now a lot not only in terms of research, but also looking to see what other companies are doing in terms of innovation. Now, the problem with innovation is that it requires most of the cases either in research or a large investment. And therefore, it's not doable for a company or even for ourselves to buy all time the last innovation that you have in the market or that you have available in terms of knowledge. Therefore, you need to define a rule of when should you invest in this new product, in this technology innovation, taking into account the price of this investment, but also the return. So that's the basic problem regarding technology innovation. And why technology innovation? Because in the way that we see is that, well, you have a certain curve that follows the trend of your price, for instance, of a product. But every time you have an innovation, you have an upward jump. And therefore, it seems that a Levy process, a jump diffusion process, could be suitable to model this. Or it could also be the other way around. You are selling a very nice product, but then there was some innovation from some competing company, and therefore people are not so interested in your product any longer, and therefore you have a substantial decrease in your demand. In this, the problems that I'm going to show, there is no competition. You just look at one company and you are just looking at investment of that company. But in fact, in real life, you could have a kind of mixed risk events due to competition and to other effects. Okay, now what I'm going to show you, it can be placed in two categories. You can either have a pure jump process where you don't have this diffusion. We have already seen, or I try to motivate with this plot, that when there is no diffusion part, then you need to check the candidates of solution. You need to check only for continuity, not for smoothness. But the fact what happens is that if you have just jumps, it means that you can go from the continuation step to the stopping step by a jump. So it's the boundary is not heated, you just jump or cross the boundary, and therefore you take the decision. Okay, I will show you two examples. One of the example is just a pure Poisson process where the jumps follow a Poisson process, and then I will show you with a non-homogeneous Poisson process, which, by the way, is not a Levy process because you don't have the stationarity any longer. But okay, let's relax a bit the definition of jump diffusions so that I include also a non-homogeneous Poisson process. And then you can also have other problems where you have jump diffusions, where you have, in fact, this continuity along the way, except once in a while you have these extraordinary events, and therefore you have these jumps. And in that case, you can enter the stopping region by two ways, either in a kind of smooth way because of the diffusion, so you hit the boundary of the stopping region and you stop, or on the other way, you can have a jump that leads you directly from the continuation to the stopping region, and therefore you cross the boundary. Okay, so the first model, it's already from the 90s, and it's one of the most cited works in terms of this Levy process in optimal stopping problems. It's from Farzin, Hausman, and Court. And it's a very simple example, and it's a very good exercise, especially for those who are starting research on to learn about optimal stopping problems. So you have these innovations occur according to an homogeneous Poisson process. Let lambda be the rate. I denote by theta the stochastic level of the technology. And every time there is an innovation, the level increases by U. And in this presentation, I assume that U is fixed, although the authors also consider random jumps positive all the time. I'm assuming the cost of adoption is I and the revenue is pi I. So therefore, what I want is to find what level. So imagine that right now I'm producing at a level which I call epsilon. That was when I took the investment, my initial investment, that was the current innovation. So right now I'm having a return which is equal to pi of epsilon. Then I have the discount rate. And then I want to find this tau, or the level of technology, the level of theta, that justifies that I move from this epsilon to a new level of technology. And with this change, with this investment, my profit, my revenue is pi of theta at this time tau, and then I pay this investment cost I. And this is a particular simple example because my pi keeps fixed until it's equal to a constant term, let's say pi, until time tau. And then when I do this investment, it also keeps fixed, so it does not change with time, but it's equal to it's a function of the technology level at the time that I decide to take the investment. Okay, so this is a particular simple example. And for this particular simple example, we are able to do a lot of things. First of all, let's call tau star the level of technology that justifies the switching, which we can prove that under certain conditions on this pi function, namely in terms of convexity, is unique. Then, in fact, how do we solve this problem? Well, it's interesting because you need to have a kind of, you propose, in fact, a solution, and then you check. So if you think of, so imagine that tau star is the level at which you should optimally change from your current technology to theta. Now, if the current level in the market of the technology is theta, and this theta is smaller than theta star minus u, it means that even after the new jump, the next one, it won't be able to justify the investment. So you just wait, and that's exactly what you see here. So this is what you get from using the current what you have now, and this is the value of waiting. Then, if you are in a region which is between theta star minus u and theta star, it means that after the next jump, which you don't know when it will happen, but you know for sure that you will change, and therefore you just sorry, I have sorry, I was just checking because of the chat. Sorry. Now I cannot go back. Oh, sorry. Okay, so this means that after the next jump, you will for sure take the investment, and therefore that's what you get. If the current value of theta is already larger than theta star, then you invest right away. And then you are able, I'm not going to show, but you are able to show that this is exactly the value of the solution of the problem. Moreover, because of this continuity that you require in this V function, you know that this theta star has to be such that this red part is equal to the green part. And therefore, you get a condition that you need to theta to justify. So in this case, it means that with kind of very simple calculations, you are able to find the value function as well as a threshold. And of course that now if you plug in different functions of pi, in some cases you can have an explicit solution for theta star, in others you can't, but that's not a big deal. The bottom line is that I'm able to solve this and I'm able to prove the optimality. Now let's change a bit the problem. Okay, 5 minutes, okay. And I'm going to assume that my intensity rate is not constant. So until time delta, I have an intensity rate equals to lambda 1. And if delta time units have elapsed since the last jump, then my intensity rate changes to lambda 2. Okay. Of course, that it means that in this case, I need to keep track of the time. And the problem is no longer stationary, but we will solve it anyway. Now, one of the major difference between this problem and the previous one is that in the previous one, you just need to take in to take the decision, invest or not invest, at time of arrivals of the jumps. Otherwise, it's not worthwhile to take the decision, so you just wait. Here, it's not the case. So here, in this case, you should take you should assess the investment decision at several times, not only at the times where you have a jump, but also after delta time units have elapsed. And we are able, so this is a problem that has been, it's based on a paper from Achspiel, Hausmann, and Nunes, and we were able to prove that the set of decision moments is different from the previous one, just by the introduction of this function, this indicator function that depends on time. Now, how do we derive the optimal strategy? Well, in this case, it's more difficult to do that because we have these several times of decisions. So first of all, if a new technology becomes available less than delta time units, since the last one, you need to check if it's worthwhile to do the investment or not. And in fact, here you get an equation that defines when is it worthwhile to take the decision to investment. And I denote this value by θ1 star, and in fact comes from the fact of putting equal the investment return. So if I invest at θ1 star, and at the other side, what happens if I postpone my decision until time delta, okay? And I have two components where one, this component means that the new technology will happen delta time units before the next one, and the other one means that no, I will have to wait at least more delta time units. So this is the first threshold that I need to check. Now, let me just move, because this is now there is a second threshold, which is the following. Okay, so I had a jump at a certain time, and my level of technology was not enough. So I decided to wait. Now I wait, and now I need to assess again my decision and time delta. And when I assess my decision and time delta, it means that I'm checking another threshold that I call θ2 star. And θ2 star, now it's exactly the same as in the previous problem that I show you, the first one, because after delta time units, my intensity rate does not change. And therefore, I have a similar equation for θ2 star. And then I'm able to characterize my optimal policy. So first of all, if lambda1 is smaller than lambda2, then I will only invest at times of arrival of arrivals. So I don't need to define this θ2 star. I just need to define this θ1 star. And as soon as the current level of technology is larger or equal to this θ1 star, I invest. Why? Because lambda2 is larger than lambda1, which means that I will have to wait longer for the next jump, and therefore it's better that I invest. Now, on the other side, if lambda1 is larger than lambda2, it means that it's very likely that I will have a new technology delta time units before. And therefore, I have not only this θ1 star, but also this θ2 star. So that's exactly what I'm trying to show you on this. So imagine that, so this is the second case. So I had one arrival, which was smaller than lambda, but it's not, I'm still at the current level smaller than θ1 star. So I have this, and now for the first time I had an arrival of a jump, which took me more than delta time units to occur. But the thing is that it did not lead me to a very high level of technology. Therefore, I don't invest now. So I wait longer until next jump. And the next jump, it is larger than θ2 star, although it's smaller than θ1 star. But as it's larger than delta, then I invest at time delta. Okay, so this is more tricky to understand, but anyway, it's just by changing a bit intensity rate. So I imagine that I don't have time for the other example. The other example, it's much more complicated, and it comes from a recent paper with many authors that you will see at the end, because I don't have time. And I'm trying to introduce now another process, which is a deterministic process. It's just an exponential decay. And in that case, the kind of reasoning that I did for both previous problems, it's very similar. So we need to take, let me just show you, for instance, one thing. For instance, in this case, I might, so in this case, first of all, the threshold is not just a threshold, is a function. And I may go from the continuation to the stopping region by different ways. For instance, imagine that I'm 2 jumps away from the optimal stopping set. Then I may enter it because I had 2 jumps, or because I had 1 jump and then my process, the deterministic one, decreased enough, and therefore I hit the boundary because of this decrease. Or it's just I didn't have any I had a decrease and then I jump and I enter in the stopping, or I didn't have any decrease and I just had I didn't have any jump and I just had a decrease. So it's kind of tricky to solve these problems, because you need to understand what kind of you need to propose a shape for the stopping region. But then, when you have this proposal, you may figure out what kind of movements, all the combinations that will lead you to the continuation and to stopping. And I'm sorry, I don't have time for this example. Let me just say that jumps, in fact, are important for investment problems. And therefore, even though they are quite challenging to solve, well, we need to take care of that, especially now that we see that things can turn out very difficult with pandemics and extreme events. So thank you very much for your attention, and I have some of the reference here. Okay, sorry. Thank you, Carlos.
Okay, thank you, Claudia. Very nice presentation. So I think that we have time for a short question. Let me just see if there is any in the Q&As. No, the remaining authors, do you want to make a question to Claudia? So it seems not. So let me just make, it's not a question, it's like a question slash comments. So in this, well, I work with you in this type of model. So I will ask you a short comment about that difficulty that we sometimes have, because in problems that you have shown, if I'm not wrong, we jump for the right side. Mm-hmm. Mm-hmm. But what can we do if we jump in the wrong side, for the wrong side?
Yeah, so that was one of the problems that I wanted to mention, is that in some cases, especially, well, even in the deterministic case, the thing is that when you jump, so the question of Carlos is, okay, if I know that I'm in the continuation region, but I jump and I for sure I stay in the continuation region, then it's solvable. That's the examples that I show you. But in fact, what happens? Let me show you here. So this is more or less, we had already this type of problem, but we managed to solve. So imagine that you are over here and you have jumps. So here in these plots, the jumps are these dotted lines. Now, when you jump, imagine that you are over here and you may, so in this point, and the jumps may be positive and negative. Here, as we knew that they were positive, I knew for sure that as soon as I jump, I will go to the stopping region. So perfect. But if the jumps are random and they could be negative, I don't know if I go to the positive or the negative region. And therefore, I end with a local differential equation, which means that the solution, it's even more complicated and I cannot find analytical solution. There exists one solution, but so far nobody has been able to solve, and therefore you need to use a numerical or quasi-numerical techniques to solve this. So this is really something that is related with these non-local, this existence of non-local points of neighborhood. So it means that the solution of a point depends not only on the value of the function f of the neighborhood, but also on of other sets. And that's a major
that's difficult, interesting, but difficult. Okay, so I think that there isn't more questions. So that's the end of this session. Thank you all for attending this session. Let me thank all the speakers. So if my colleagues if you don't see any problem, you can turn on your cameras, because I can take a screenshot or something like this, just to stay with the picture of us, and afterwards I will send you this picture. So I'm very bad with this, so I will try to take this print screen, and so let's see if this works. If this works, I will send you the picture. If not, we stay without the picture. Okay, so thank you. There is more sessions in the afternoon. Afterwards, at the midday, there is another one that is a plenary section. So enjoy the Congress, and thank you for being here.
Thank
Bye.
you.
Thank you.
Bye, everybody.
Thank you.
Bye-bye, thanks.
Thank you.